In this video, I'm going to make an introduction to the topic of limits and convergence. We're going to have three topics in this video: convergence versus divergence, limits in functions, and then limit notation. So I'm going to start with convergence versus divergence. So here we have the first sequence sequence A, which is 1, 3, 5, 7, 9. This sequence is made up of 5 terms, being A1, A2, A3, A4, and A5. So I have a question. So what happens if I continue increasing the values more and more and more? Well, they are simply gonna get bigger and bigger and bigger. So in other words, what happens if I add a 6th term? The next value is gonna be 11, a 7th term, 13. And let's say I go to a term infinity. So there's not a specific value. If we increase the values, we're going to go to infinity. So we can say that this sequence is going to diverge. Therefore, the limit does not exist. I can also draw this convergence and divergence by saying that convergence is when the numbers tend to a specific point, to a specific value, and divergence is when the sequence is heading to different values, different points. So in this sequence A, for instance, we are heading to infinity. Infinity is not a specific value, so we can say that in this sequence A, this series diverged. Therefore, the limit does not exist. Now, we have sequence B. We have, for example, 1 over 10, 1 over 100, 1 over 1,000, and so on. So we have fractions. This first fraction is, in other words, 0.1, and then 0.01, then 0.001. So if I keep increasing the terms up to infinity, to what value am I going to? Now let's say we have the value 1 over 1 million. This is also 1 over, this is also 0.00001. So as you can see, we're heading to a value. If we increase the sequence, we're heading to a number which is 0. So we can say that this sequence is converging. So therefore the limit exists, and the limit is 0 for this sequence. Now we have a sequence C, sequence C, which is 3, 4, 3, 4, 3, 4. We have this sequence, and as you can see, there's not much change. We have 3, 4, 3, 4, 3, 4. So what happens if I increase the sequence up to an infinity term? If I keep increasing the values, well, I'm just gonna get more 3 and 4s. So this sequence, we can observe that it's not going to a specific value. It's alternating between values. The sequence is divergent, therefore the limit does not exist. Now we're going to see the second thing in the agenda, which is limits in functions. Now I have here the graph of f of x, 1 over x plus 1. We have a domain, all real numbers except -1. We can take all values in the real numbers, but we cannot take -1. Taking -1 would mean 1 over -1 plus 1, which is 1 over 0. This would invalidate the function because we have a 0 on the denominator. As you can see, I have the function drawn here. This is hyperbola. We have here all values are taken except for this line, which is in -1. As you can see, the values are getting closer and closer and closer to -1, but they really never touch -1. As you can see, if you take values that are greater than 1, for example 0.5, you have here this value. If you take values less than -1, for example -1.5, you have negative numbers. So if you take values greater, we can see that they are going up to infinity. If you take values lower than -1, they are going to negative infinity. So they are heading for different values. This function is divergent, therefore the limit does not exist. Now we have here a second example, example 2, which is f of x squared minus 4 over x plus 2 with the domain all real values except for -2. We can see that the function behaves linearly, and we can see over here in this point, which is -2, I have a little circle there in blank. Is because the function is invalidated when it's -2. And we can see this is called a discontinuity because the function has a gap. It has a jump in -2. It doesn't take -2. So we can see here that even though that there is a discontinuity, we can see that if we take values less than -2, for example -3, we're heading somewhere. We're heading to -4. If we take values more bigger than -2, for example -1, we have a value. Even though there is no that defined f of x, function of x for -2, the surrounding values of the function does have values. For example, here and here, we do have values at those points. So even though there's a discontinuity, we can say that the limit of this function as it approaches -2 is -4. Now, looking at some notation of limits, limits are written as the following. So we have lim, which stands for limit, as x approaches a. A can be any value. A can be 0, 1, 2, 3, negative numbers, fractions. So we have limit as x approaches a of f of x, which is the function. For example, the limit as x approaches -2 of x squared minus 4 over x plus 2. So this is basically asking, as the x value becomes sufficiently close to a, or in this case to -2, as it becomes sufficiently close to -2, I get closer and closer and closer to a f of x, to a value in y. So this is, as I get closer and closer to -2, I'm getting somewhere closer and closer in the function. So this notation over here can also be the limit as x approaches a of a function, let's say x squared equals L. L stands for a number. L can be any number. L is the resultant. L is the limit. So further examples and explanations to specific problems will be in the next video. Thank you.